Alright, so here it is, last video. I'll try to keep it under an hour. It's so hard to say goodbye sometimes. Um, Even though you have a final and stuff left. It's not over, but yeah. My workload's gonna go down a bit. Um, so we're gonna talk about pushing equilibrium systems around. How do they respond? So we're gonna talk about shifts. So when you perturb, when you mess with an equilibrium system, and you push it off of equilibrium, well, remember, equilibrium is spontaneous. It's just going to return to it. So it's going to make changes. It's going to shift back to equilibrium. And now we're only going to talk about this for gases, but I will say, just as a kind of a throwaway comment here at the end, that every trend we talk about here, except for the ones with pressure, are going to hold for aqueous systems. So stuff that's dissolved in water that's at equilibrium, the trends will hold. Except for pressure, because changing pressure doesn't really affect, liquids, right? Things that are dissolved in liquids fall in the same boat. So, if we, I guess I'll write this out because it is, my everyday language version of Le Chatelier's principle. So, because equilibrium is reached spontaneously, which we've talked about quite a bit, so hopefully that's not news to you. If we have a system that is pushed off equilibrium, well, then it's going to return to equilibrium because it's spontaneous. And we'll talk about how it gets there. It's a journey. Now this is known as that's a little pointy thing. Le Chatelier's principle. He's French. In case you didn't know, I'll try not to bust out my horrific fake French accent. Now, I will say Le Chatelier is an interesting chemist because he's kind of almost more of an accountant. He was in charge of, this is no joke, he was in charge of Napoleon's armory. So he'd be like, oh yeah, we have 10,000 cannonballs, and then we fought, Bulgaria or something, and now we have 4,978 cannonballs. Like, that was his job. And so it actually really helped with the understanding of equilibrium, because equilibrium can kind of be thought of as like, accounts receivable and accounts payable sort of situation. You pay bills and you get paychecks. What's the balance looking like? Well, that's equilibrium to an extent. Is you have products and reactants, and what do they look like with respect to each other? And so that actually gave him the skill set to really look at equilibrium, which is interesting because it's something not directly related to chemistry. And it's one of many scientific breakthroughs that actually came from Napoleon's army, of all things. You can thank him for canned food, too, because he's like, how do I get food to soldiers? And then they're firing cannonballs at those Bulgarians. What do I do? Well, we'll put it in cans and move it, and then we don't have to find food everywhere, when we're moving through the countryside. A lot of things like that. So, yeah. But he never played Risk, so he didn't know not to go into a land war in Asia. Alright, so, a system's just going to shift to return to equilibrium. That's the idea here. You mess with it, you push it off its spot, and it just rolls back. That's what happens. So, how do we push a system off equilibrium? Turns out we have a few options. What can we do? What do I mean by push a system off equilibrium? Well, we have to do something that causes concentrations to change. Well, the first option is kind of an obvious one for changing concentrations. It's just changing concentrations. I add more reactant, or I pour some of the product in, or I remove some reactant, or I remove some product through a process. And that's going to push it off equilibrium. My ratios are going to change from the equilibrium values, and it's going to have to adjust to compensate. So, changing concentrations, which means, adding or removing products or reactants, just whichever. Alright, and so if we look at an example here, I think you've seen this example before. So if we have 3H2, I'm introducing a new principle, no need to introduce new chemistry, right? No need for a new reaction. Then we get 2NH3. You guys are just so familiar with ammonia now. You're ready to start your own fertilizer plant and blow up a chunk of Texas. I think I've talked about that with you before. They have a bad habit of that there. They have a bad habit of, where else was the other one? It was in the Middle East somewhere. It was in Lebanon, I think. Yeah. They had a big blow up too. So fertilizer plants can spontaneously explode if you don't store things carefully. In the United States, it always seems to happen in Texas for some reason. It's almost like you need regulations on how to store fertilizer, or people don't do it right. So, what can we do here? Well, we can add more H2. We just pump some more H2 gas in there. Everything's at equilibrium. We pump some H2 gas in there. What happens? Well, we've increased the concentration of our reactants. Right? So what does that mean? That means that our forward reaction rate is now faster than our reverse reaction rate, and they have to equalize. So we're going to form more products. Which we call a shift to the right. We're going to make more stuff over here. It's shifting to the right. And it's going to do that until it reaches equilibrium again. We could also add more into. Same effect happens. What if we remove a reactant? What if I find a way to remove into gas from this reaction vessel? And I do that. What happens? Well, now I have a lower concentration of reactants, and they need to be replaced. So it's going to be faster in the reverse reaction, and so it's going to form more reactants. And so guess what we call that? If we move this way, it's a shift right. Well, if we move this way, it's a shift left. Okay? So, adding reactants causes it to shift right. You're pushing it right. If you remove reactants, you're pulling it left. You're kind of creating a deficit that it has to fill. Whereas you have a surplus that it has to burn through if you add them. Okay? Well, what if we do the same processes with products? What if I end up adding more NH3? So I'm increasing the concentration of products. Well, it's going to have to form more reactants to compensate. The reverse reaction is going to be faster. And guess what we call a situation where we form more reactants? It's a shift left. Now, what if I remove NH3? Well, then I'm going to pull it to the right. So it's just like the reactants, just the opposite. So if I remove a product, it's going to shift right. If I add a product, it's going to shift left. Just like if I add a reactant, it's going to shift right. If I remove a reactant, it's going to shift left. It's all about balancing, okay? So if I remove from one side, it has to shift to compensate. If I add to one side, it shifts to compensate. If I remove from the other side, it shifts to compensate. If I add the other side, it shifts to compensate. Doesn't matter what side it is. It just shifts however it needs to balance out at equilibrium. Okay. And one way I think of it is, if I overload a side, I'm pushing it the opposite way. If I remove from that side, I'm pulling the reaction towards it. It's kind of like a trick of language I like to use. Okay. So, what about our second option? What might that be? Well, we can change temperature. I talked about that a little bit. Let's talk about it in a little more detail. So you can heat stuff up, you can cool it down. Well, this will work to shift equilibrium if our process is, endothermic or exothermic. If it's in the middle, then this doesn't really do anything. So, for example, let's look at our old friend again. So H2 plus N2, you're probably getting so sick of this reaction, but it's okay, there's going to be a new detail. I've been hiding something from you. Heat is also a product. This is an exothermic process. Now, how do you know that? Because I just told you. You could look it up as well. If you look up the delta H for this reaction, you'll see it has a negative value. So it's an exothermic process, which means heat is a product. So, heat is a product. Alright, so if we increase temperature, that's adding heat, which means we're adding a product. Alright. Which means if we increase the product side, it's going to shift left to compensate. So it's just like increasing concentration in NH3. It's like I'm increasing the heat. I'm increasing a product. It's going to shift left to compensate. Conversely, if I lower the temperature, then I'm removing heat, which is the same as removing a product, because heat is on the product side here, which means I am going to pull the reaction to the right. Okay? And it's all because I know that heat is right there. That's how I'm able to determine this. So what about an endothermic process? Well, then heat becomes a reactant, and so then we're adding or removing a reactant. And so this whole thing reverses for endothermic processes. Because heat is a reactant. So just be aware of that. But what you can do is, if you understand the concentration stuff, it just falls right in line. You just ask yourself, is heat a product or is it a reactant? And then you go, am I adding a product? Am I removing a product? Am I adding a reactant? Am I removing a reactant? And it adjusts just like if we were adding or removing in terms of concentration. So that's very nice. Now, if there isn't really heat as a product or a reactant, so it's not endothermic or exothermic, then there's no change. But that's very rare. Okay? So that brings us to our last option, which is pressure. So everything I talked about before would work for an aqueous equilibrium, some water-based, aqueous species dissolved in water. This is the only one that's unique to gases. So just a heads up on that. And that is changing pressure. Because gases are compressible, they'll respond to changes in pressure, and other phases of matter do not. So, before I get into the example, This is a nice, straightforward rule. It's not situational. I don't have to ask, is it endothermic or exothermic? I just go, alright, well, increasing pressure is going to equal favoring the side with the least gas particles. Alright, so what does that mean in practice? Well, let's look at a reaction. I wonder which one I'll use. Make some ammonia. Have you memorized the process yet? Alright, so I look at this and I have 1, 2, 3, 4, because there's 3 H2s and 1 N2. So there are 4 gas molecules here. And I only have 2 here. Alright, so time for one of those tough questions. Which number is smaller? 4 or 2? So 2 is less than 4. Alright, so what does that mean? Well, if I increase pressure, I'm going to shift right. Because that's where there's less gas particles. Now, why does this happen? Well, this is going to take up half the space of this. It's not about the size of the gas particle, it's about the number. Remember the gas law, PV equals nRT. N over here is half of what it is over here. So they're gonna have half the volume they occupy. So because there's 2 NH3s that take up, or because 2 geez, getting to the end of the night, I guess. 2 NH3 gas particles are going to take up less space. By the way, I think day 1 I promised I wasn't going to edit stuff like that out, and I am a man of my word. So they take up less space than our reactants, which are 3 H2s and an N2. So it's kind of like it's getting crushed into being NH3. It relieves the pressure. Okay. Now, if I were to drop the pressure, then it would shift towards the side with more gas particles. So the opposite is also true. So if I increase pressure, I shift right. If I decrease pressure, I will shift left. Now, one little note here. This is only going to occur when we are compressing or expanding the volume. So there are other ways to increase pressure, such as adding an inert gas, and that doesn't do anything. So doing this will, increase or lower the pressure, depending on whether we're expanding it or compressing it. And so the takeaway is adding an inert gas has no effect, because our partial pressures because our partial pressures are unchanged. All right. So that doesn't affect equilibrium. So only changing the volume to increase pressure, decrease pressure overall, because that's actually going to shift our partial pressures around. And so just a heads up, if you do any other trick to increase pressure, it doesn't work. Alright, so before we call it a day here, let's make sure this makes sense. Let's put this all together. let's look at a new equilibrium process, and let's ask a very straightforward question about it. Alright, so let's say we have 2H2 gas plus O2 gas. And this can go into an equilibrium, believe it or not. It's this H2O gas and 2 of those. Okay. So we got a new equilibrium system. This is the one responsible for blowing up Fukushima. This is the reaction responsible, I should say. The chain of events that led to this reaction being able to blow up a giant concrete sarcophagus monolith thing is a whole other story. there's a tale behind this. But if you watch the video on YouTube or you saw it on the news or whatever, and you saw the reactor containment vessel explode open, that was actually H2 reacting with oxygen to do it. And the reason was because when the reactor overheated, it created conditions where H2O could actually decompose back into H2 and O2 gas, and then conditions would arise where they would turn back into H2O and do so explosively. It's a lot of energy released. So the other detail is when you do this, heat is a product. So this is a combustion reaction, and it releases heat. So I promised you a question about this. Allow me to deliver. How can we make this shift left? What can we do? How can we make equilibrium more favorable over here? How can we make more H2 and O2 show up? So why don't you think about those three things we talked about? Maybe pause this, take a crack at it, and then I'll go through it with you. Alright, so the first thing we can do, at least in the list that I organized, so maybe you went in a different order, that's fine, okay. But we can change concentration of reactants. Alright, so we could lower our concentration of H2. We could start siphoning H2 out of the system. Or we could do the same thing with O2. And that's going to cause it to shift left. We can change concentration of products. We can put more steam in it. So we can increase the water vapor concentration, which, by the way, because this is a gas, it shows up in our KEQ expression. Only liquid water does it. Or solid. Ice wouldn't either. But gas does. It participates in the equilibrium. Alright, so we can, change concentrations. We can also change the temperature. So which way would we have to change this temperature? Would we heat it up, or would we cool it down to go over here? Well, heat is a product, so we want to overload the product side to shift left. So we're going to increase the temperature. We're going to add heat. Alright, and then does this respond to pressure changes? Well, it's a gas, and I've got 3 particles over here and 2 over here, so yeah, if they were both the same number, it actually doesn't. If it's 2 and 2, if it's a tie, changing pressure has no effect. But luckily it's 3 and 2, so we can also change pressure. Alright, but if we want to get over here, do we want to increase pressure or decrease pressure? What do we want to do? So there's 3 on the left, 2 on the right, so if I lower pressure, it's gonna shift left. If I increase pressure, it's going to favor the side with less gas particles. So if I do the opposite and I drop the pressure, we go over here. Alright. And this is because there's more gas particles to the left, which means we have to drop pressure, as you can clearly see. Alright, so hopefully this makes a little bit more sense of the changes of equilibrium and how we can manipulate a system to shift based on changing concentrations, changing temperature, changing pressure. And, you know, these are tricky ideas, but maybe seeing it all put together like this was just kind of the little final piece you needed to make sense of it, hopefully. If not, there's a practice sheet. Maybe you just gotta, you know, noodle around with that a little bit. But that's the end of the class material, by the way. This is it. So we made it to Le Chatelier's principle. We went from matter is stuff that takes up space, and then we started talking about balancing these equilibrium processes and how we can push them around and how they respond. I mean, just this right here. Think about how far that is from where we started. And then to be able to talk about all this on top of it, like, that's a pretty good semester. So the details for the exam, I'll have a module for that. Please, any questions you have as you're studying, feel free to stop by my office hours or make an appointment to meet with me. I'm happy to do that. And I wish you the best of luck. And I will also have a link to evaluate the course. So I do value your input. So, you know, like me, hate me, rate me, or if you're indifferent, you can rate me too. That's fine. And the main thing I ask is, you know, whether it's positive or negative, you know, try to be detailed so I can understand. Like, if you're just like, I hated your class, or, you know, I really liked your class, that's great. Either way, that's cool. You know, I'm glad that you stuck in there for something you hated for so long, or that you stuck in there and really enjoyed the class for, you know, 16 weeks. It's a long time. But tell me why, so I know what to keep, what to change, what to adjust. This is the first time I've taught this class, so it is very plastic. There's a lot that I can move around. You know, after I teach something like 10 times, it starts to be a little bit more solid. But right now, you know, I'm very open to suggestions, especially since I'm still relatively new to the online teaching. All of my experience has been since since the world shut down. So, and, you know, any suggestions there, let me know. I do plan to build more material out in the course the next time I teach it. But I would value your input on that as well. So, you know, if I don't see you in an office hour or in a WebEx meeting before the exam, good luck. Have a good break, and you know, best of luck in your future studies. And, you know, if there ever is anything I can do to help you out, you're on Team Joe. You can always message me, and I'll be happy to respond with, who is this? No, just kidding. To help in any way I can. All right. So, good luck as always.